All right, this is the video for Geometry Unit 6, Lesson 2. There's a lot of proofs in this lesson, so I'm actually going to, like I said previously, whenever we come to proofs in our material, I'm going to work through those on these videos and just kind of explain how they work for you guys. There really aren't any of those on the test, but it's kind of helpful to hear the logic and see how a lot of these properties are applied to actually doing, geometric proofs. So please make sure you check out the lecture notes. I've posted what I did in the previous lesson here, and then as well as the actual images of the different theorems that you'll be using. So we're going to be looking at the lesson 2 theorems here. So they're all on this kind of the second page of this notes. So we'll kind of refer back to this as we go. So kind of just leave that there. Zoom out a little bit on that. So hopefully that'll be helpful to you. And then like I said, I'm going to work through some of these problems. So this second lesson is the opposite of what we talked about in the last lesson. So in the last lesson, the material was focused on what are these properties of parallelograms that we know all parallelograms share. And we went through those, and that's what you saw here in the examples. And then, of course, these are the 4 theorems we went over. So the theorems from 6.2 are the opposite in that they are what say, like, if you can prove, for instance, that the parallelograms have opposite sides that are parallel and congruent, like you see here in theorem 6.2a, if you can prove that or show that, then the thing you're looking at is a parallelogram. So it's kind of the reverse of the thought process as in the first lesson. So we're going to be doing that through different proofs. So we're going to talk through that here. Says we are given a quadrilateral, A, B, C, D. We are given the fact that BC is parallel to AD. And we're given that BC is congruent to AD. And the thing we have to prove is that because of all of this, can we prove that ABCD is a parallelogram? So again, as with all proofs, the very first thing you're going to put is going to be the givens. That's already shown for us. We have everything we just talked about given. Then it says angle 2 is congruent to angle 4. So how are we getting that? Well, this is going to come back again to like an idea from geometry that we've learned in the past. We have this angle and this angle. So the thing you have to realize is that what we're looking at when we have this is we are looking at, again, 2 parallel lines with a line cutting through it. Let me erase that real quick. That should look familiar to you. That is what we call a transversal line. Again, the transversal line deal tells me that different angles within this diagram are congruent. One pair that is congruent are these two right here. And those are called alternate interior angles. So alternate interior angles is what's referred to here, angle 2 and angle 4. So when they tell us that, that's the reason for that. So let's go here and we see if that's in here. There it is. Alternate interior angles theorem. Now again, I'm doing this because I know that there are a lot of you who may not remember those concepts from earlier, but hopefully that maybe sounds familiar to you. So that's how we prove number 2. So let me keep going. AC is congruent to AC. Okay, anytime you see this idea where you have the same thing congruent to itself, that is called reflexive every time. So reflexive always refers to something being congruent to or equal to itself. So that one's pretty straightforward. Always going to be reflexive anytime it's something equal to itself. All right, so then we go to the next one. Triangle ABC is congruent to triangle CDA. Let's go up here. So triangle ABC, that's going to be this guy, is congruent to triangle CDA. CDA. Okay, you can see those 2 triangles there. And the question is, how are we able to prove that? Well, we've already proven that angle 2 is congruent to angle 4. we've already proven that this is congruent to itself. And then we already know that this is congruent to this. That was one of our original statements. So combining this, this, and this, those lead to number 4. So then how do I know what theorem it is? Well, we see we have a side, we have an angle, and we have a side. There's only one way to use those three in conjunction with each other, and it is side, angle, side. Look at that. So convenient. So that's going to be what you have for number 4. So let me erase all that right there. So we've now proven that these two triangles are congruent because we want to show that the other sides are parallel as well. Let's see how we get to that. So we go down. Number 5, angle 1 is congruent to angle 3. Okay, so hopping back up here, angle 1 is right here. Angle 3 is right here. That should look familiar to you because we used that same idea previously with angle 2 and angle 4. So let's go down and see what we got here. It says hint. It starts with C, ends with C, has a C in the middle. Well, that's pretty obvious which one's going to be. Maybe it's CPCTC. I think so. Now, CCC theorem is nothing. I don't know what that is. That's completely made up. It's there to throw you off. CPCTC stands for congruent parts of congruent triangles are congruent, because we see here that our triangles that we already proved were congruent have other congruent parts. If those two triangles are congruent, if they're the same, then every matching part is the same. The sides that match are the same, the angles that match are the same. And so 1 and 3 is just another example of two parts that are on that triangle. So those parts have to be congruent. Next, AB is parallel to CD. Well, how do we do that? Well, actually, what's happening is the move from 5 to 6 is the opposite of the move from 1 to 2. So here we move from parallel lines to congruent angles. Now we're moving from congruent angles to parallel lines. Well, then it has to be something like what we have in number 2. So let's look. Converse of, there you go, converse of the alternate interior angles theorem. Notice there's a connection between 2 and 5, or 6, 2 and 6. And then lastly, that is all we need to prove that ABCD is a parallelogram. All right, thanks for bearing with me on that. So let me clear everything and move on to our next thing. So make sure you get all of those entered. This is just more of the same, different theorems. This is now theorem 6.2b, which is the opposite of theorem 6.2a. So they're giving us the theorems that are the reverse of the theorems from the previous lesson. So I'm just going to blow through all of this, jump down to this next proof. Similar idea. We have a theorem, or a given, of quadrilateral ABCD. That's the quadrilateral you see in this image. A and C are congruent. That's these two angles. D and B are congruent. That's these two angles. And so we have to prove that it's a parallelogram. So slightly different. We're starting with the angles now. So let's look here. Angle A is congruent to angle C, or equal to angle C, and the measure of angle D is the measure of angle B. Now this is kind of a weird statement because that looks very similar to what we have right here. But actually what we're doing is we're converting something that is congruent and changing it to something that's equal. So there's a difference in geometry between congruent things and equal things. So we're dealing with the difference here. So we're trying to get from congruence to equality. And whenever you have that, it's always going to be the definition of whatever this is. So in this case, that's congruent angles. Okay, congruent angles, by definition, are angles that are the same measure. So anytime you have this jump from congruent to equal, you're looking for the definition of that object, in this case, congruent angles. Then we go, let me erase. Then we go to our next one. It says angle A plus angle B plus angle C plus angle D equals 360. Well, that's just plain and simple let's look through here. What do we think? Well, it's got to be something about the angles being added together. None of the, there's angle, but that's not a theorem. So let's keep looking. Oh, there it is. Polygon interior angle sum. Angle sum. We added up the different angles. So that's kind of how we know that, because we're adding up the angles. And this theorem is what tells me that the answer is 360, the polygon interior angle sum. Again, that's coming from a previous unit that you may or may not have done. Now we look at the next one. Oh, this is a little weird. A, B, A, B. So they've changed C to A, and they've changed D to B. Now, how did they do that? Well, they did that because of this and this. If A is equal to C and D is equal to B, then I can replace them, or in other words, substitute them. Substitution property of equality. I'm substituting one value for another value because they are the same. All right, let's move on. Move on to the next one. They're just doing some algebra here. They've gone down. They've done 2 times A plus 2 times B, 2 times A plus 2 times D. So they've just simplified. Now look at what they did here. Oh, this is interesting. The 2's all went away, and the 360 got cut in half because they divided everything by 2. So they divided. Division property of equality says I can divide everything in that expression by 2. So they divided all of this by 2. And so the 2 goes away, the 2 goes away, the 2 goes away, the 2 goes away. This becomes 180. This becomes 180. That's what's happening there. All right. Pretty straightforward. That's just algebra, really. Resolve this. All right. Next. Now they say A is supplementary to B, A is supplementary to D. Definition of, I wonder what it could be the definition of, since we've just introduced this new idea called supplementary. Yeah, I'm being kind of ridiculous there because the answer is clearly supplementary angles. So we have definition of supplementary angles, and then the rest of that is spelled out for you. Okay, so thanks for bearing with me on these proofs. I'm going to take us through really quickly. All the first 5 questions here are all just definitions. So please go back up to the top and work through the different theorems, or you can use the theorems from the lecture notes over here. The lecture notes have it as well. And that's all they're asking you for in these first 5 is to fill in the blank to finish the statement, which is going to come directly from those terms. Starting in number 8, they're looking at the different pictures, and you have to decide which one goes with it. For instance, which quadrilateral shown could be proved to be a parallelogram by 6.2a? So what's 6.2a? 6.2a says if one pair of opposite sides is parallel and congruent. So I looked in my diagram. Let's see. This one is diagonals. That's not it. This one is angles. That's not it. These ones is 180 supplementary. That's not it. This shows congruent sides. This shows parallel and congruent. That is my answer. Because quadrilateral with pair of opposite sides, parallel and congruent. That's what happens in this diagram. So IJKL is the correct response for that one. So that's what you're doing in each of these. You need to match the information here with one of the diagrams. You should be able to do that by just process of elimination. Which one shows opposite sides congruent? And so on. Let's keep going. That's all those. Then we get down to a couple of proofs. I'm going to pause this video because it's getting a little long, and I'll pick back up here in a minute.